All right, ladies and gentlemen, welcome to our historical atomic theory lecture. The purpose of this lecture is to understand how the development of different experimental techniques over time led to our modern understanding of the atom. Um, the lecture that we're going through here today in class is generally a fairly lengthy lecture, and so what you're going to be hearing right now is a rather abridged version of the lecture which we do in class. So let's go ahead and get started. If you think about our modern understanding of the atom, we know an amazing number of different things about these incredibly small particles, which we fundamentally have difficulty seeing on the human scale, which we're used to. And so the purpose of what we want to go through today is to understand how it is we know so much about atoms when fundamentally none of us have ever seen an individual atom with our own eyes. And the key idea that we're going to get at today is that the developments that have been made over time each have built upon previous ideas that were proposed by scientists. The phrase that we use in science is that we are standing on the shoulders of giants. That is to say, we can reach deeper and deeper into our understanding of how atoms work only by building off of the amazing ideas that have been proposed by previous scientists who come before us. So, we're going to go and start way back in the day here for our early discussion of how we first came up with this idea of atoms. And we're going to go way back to kind of the dawn of Western civilization in terms of the ideas proposed by some of the early Greek natural philosophers. These philosophers are fundamentally not scientists. That is to say, they were not performing experimental science in the way we understand it today. They like to sit around and think through their ideas, and to the Greeks, who praised really logic above pretty much all else, if an idea made logical sense, then it was most likely to be true. So these Greeks were really more interested in logical argument than in experimental evidence. The first of the Greeks we're going to talk about here is a gentleman by the name of Democritus. Democritus proposed an idea that matter was made up of two different things. Number one, empty space, and number two, something he referred to as atomos, which is a Greek word for indivisible. Those atomos, or indivisible particles, were an idea he came up with to explain a thought experiment. And what Democritus thought of was this. He essentially said, if you start with an amount of matter, and then cut that amount of matter in half, you'll have two smaller samples of matter. And then if you cut those halves in half, you'd have yet smaller and smaller and smaller samples. And to Democritus, it seemed that it would be impossible to divide a sample of matter in half an infinite number of times, which meant to him there must be some indivisible amount of matter that existed, that when you got down to a smallest chunk of matter that small, it could no longer be separated into two distinct parts. And that thought experiment was obviously never something he actually went through and did himself, but it led him to come up with this idea that matter, in fact, was made up of indivisible unit particles. And we derive the name today for our atoms that we know from that Greek word atomos, again, which means indivisible. Now, a follower of Democritus was a familiar philosopher, you've probably heard this name before, who is Aristotle. Aristotle rejected the idea of atoms, which was proposed by Democritus. He did, however, bring up an idea that we would come back to later in modern science, that matter is composed of different elements or different fundamental unit particles that he referred to as the constituents or components that make up the world around us. The elements that Aristotle identified are listed here on your slide here. They were earth, fire, water, air, and the ether, which is this kind of insubstantial substance that he thought permeated the space and heavens above him. He didn't believe that any of this was actually in the form of atoms. Now, today we recognize that those 5 different substances identified by Aristotle as elements are certainly very far from it. Earth, obviously, is a mostly heterogeneous mixture of different materials. Fire is energy. Water is a compound, so at least we have a pure substance now, but certainly still not an element. Air is a homogeneous mixture, and ether, as it turns out, doesn't even exist. So of his 5 elements, he got 0 correct. But he had this idea that you could take different parts of these different elements and mix them together to form all the matter of the world around us. For example, if you thought about wanting to make, say, a tree, trees grow out of the ground, so there was some part of earth inherent in the tree. Trees also are responsible for um, taking up water out of the ground using their roots, so they were made up of some component of water. And when you take wood and you light it on fire, it releases that energy, the fire, so he thought there must be some fire inherent as a quality to the tree itself. So in his mind, the tree would compose parts of earth, fire, and water, and you can mix them together in the proper ratio to produce a tree, which obviously we know today is nonsense, but the idea that we can combine together different elements to make the substances around us is an idea that would come back later on. So again, neither of these two ideas were supported by experimental evidence, but more by logical thought arguments. And so we don't count these really truly as science, but more as what we refer to as natural philosophy. Now, following the Greeks, we had a fairly lengthy time of kind of spirituality over scientific reasoning that dominated Western thought, and this was what we refer to as the Middle Ages. Now, that's not to say that during the Middle Ages there wasn't interesting stuff going on, because there certainly were some people who we recognize as being kind of the forefront of modern chemistry. And these were people referred to as the alchemists. Now, much like the Greek philosophers, the alchemists weren't true scientists either. They were very important experimentalists, and they recorded large amounts of data and evidence, so in that matter, they were kind of the opposite of the Greeks. However, the roots of their thinking was very much in the kind of Middle Ages ideas of mysticism and spirituality rather than reason. And as such, they gifted to the scientific community a very large amount of knowledge, and they kind of were thought of as the forebearers of modern chemistry. Now, the alchemists were interested in a couple of big ideas. Number one, they wanted to be able to discover a magical material that would allow them to turn cheap metals, or what we call base metals, into gold. And number two, they were looking for something which they called the Philosopher's Stone that could produce a material they referred to as the elixir of life to help them live forever. And they spent a large amount of time in pursuit of these ideas, experimenting by just mixing stuff together and performing kind of experiments on matter around them. They were obviously never able to achieve either of those two goals. However, those observations and experiments which they went through and produced actually led to our modern practices of chemistry that we see today. So they were kind of on the forefront of scientific thought. And following those middle-aged thinkers, our alchemists, we moved on into what comes next, which was the Renaissance. Renaissance is a word which means rebirth, and it was really a rebirth of the logic and reason that had been championed by the ancient Greeks. And following that Renaissance, we moved into what we refer to as the Age of Enlightenment and the Age of Scientific Reason. So this is the first place where we actually see real science being done that combined together the logic and reason proposed by the ancient Greeks together with the experimental evidence that was so important to what the alchemists had been working on. And our first Enlightenment thinker here we're going to talk about is a gentleman by the name of John Dalton. So John Dalton went back to those ideas first proposed by the ancient Greeks by Democritus, that in fact matter was made up of indivisible particles, which he referred to as atoms, again from that Greek root, indivisible. He didn't believe that atoms had a charge or were made up of charged particles. He thought that all of them were neutral. And the key idea here is that this wasn't just an idea he had, it was an idea that he backed up with experimental evidence. And that experimental evidence came about through his creation of what we refer to as 3 laws. Those first of John Dalton's 3 laws should be a familiar one to you from previous science classes. The first law is what we refer to as the law of conservation of mass. And what that law says is that during a chemical reaction, matter is neither created nor destroyed in the course of that chemical process. And Dalton was able to demonstrate this idea with evidence in that during the course of chemical reactions, if you mass the mass of the reactants before the reaction occurs, and then you capture all the products after the reaction occurs, the mass of the reactants must equal the mass of the products. And he was able to demonstrate this consistently in a variety of different chemical experiments. So he had an idea which was backed up by experimental evidence. The second of John Dalton's laws, which led him to the discovery of atoms, is what we refer to as the law of definite proportions. The law of definite proportions essentially says that the mass ratio between two elements in a compound is a constant value. And as an example, let's talk for a moment here about water. If you take a sample of, let's say, 18 grams of water, in that sample of 18 grams of water, there will be 16 grams of the element oxygen and 2 grams of the element hydrogen, which means the mass ratio of oxygen to hydrogen is a ratio of 16 to 2, which comes out as a ratio of 8 to 1 oxygen to hydrogen. Then let's say you went through and you took a second sample of water, and this second sample of water had a mass of 36 grams, and then you decompose that water into its elements, oxygen and hydrogen. You would discover through that decomposition that you would have found 32 grams of oxygen and 4 grams of hydrogen in that sample of 36 grams of water. And again, that mass ratio of oxygen to hydrogen would give you, again, an 8 to 1 mass ratio of oxygen to hydrogen. And no matter how much water or whatever it was Dalton was experimenting on, when he decomposed those substances into their component elements, he discovered that the mass ratio between those elements was always a constant value. And that told him essentially that compounds are made up of some substance in definite proportions. Now, the last of John Dalton's laws that he was able to use in order to make an argument for the evidence of the existence of atoms was the trickiest one to understand here, which is what we refer to as the law of multiple proportions. Now, the law of multiple proportions also has to deal with mass ratios, just like the law of definite proportions. However, the law of multiple proportions deals with two distinct compounds, each of which are made up of the same two elements. For example, water and hydrogen peroxide. And what the law of multiple proportions states is that for two different compounds, each made up of the same elements, the ratio of the mass ratios between the elements in those two compounds can be expressed as a small whole number ratio. And let's take a look at what that really means. Through a decomposition reaction, just as we discussed before, John Dalton could decompose water into elemental hydrogen and oxygen, and from that decomposition, in water, he determined that the ratio of oxygen to hydrogen was a mass ratio of 8 parts oxygen to 1 part hydrogen. And then he went through and did the exact same experiment with hydrogen peroxide, decomposing it into hydrogen and oxygen. And in hydrogen peroxide, from that decomposition reaction, he determined that the mass ratio of oxygen to hydrogen was 16 parts by mass oxygen to 1 part hydrogen. And here's the big trick then. What he looked at then was the ratio of the ratios of the elements within those two different compounds. So within hydrogen peroxide, we had a 16 to 1 ratio, and within water, we had an 8 to 1 ratio of oxygen to hydrogen. And looking at the ratio of those ratios, 16 to 1 divided by 8 to 1 gave him a ratio of the ratios of 2 to 1. No matter what substances he tried this experiment with, as long as they contained the same sets of elements, he noticed that all of the different ratios that could be expressed could always be expressed as a small whole number ratio. Now, taken together, these three ideas that, number one, matter is conserved during chemical reactions, not created nor destroyed. Number two, that the elements which make up compounds are always found together in the same whole number mass ratios, in the same mass ratios. And then number three, that the ratios of those ratios are always small whole numbers. What that really told John Dalton is that as chemical reactions occur, matter is being moved around as unit chunks. That is, unit chunks of matter are moving from place to place, but you never get fractional ratios of matter moving around. And as such, that evidence that matter was moving as unit chunks told Dalton that, in fact, that idea proposed by Democritus of atoms was probably a reasonable expectation. And from that, we make our very first model atom, A Dalton model atom is a very, very simple looking thing. It is nothing more than a neutrally charged sphere. So that's our first idea that in fact atoms actually exist. So now that we have discussed the idea that atoms actually exist, we're going to now delve into the interior of an atom. And as it turns out, the first of the subatomic particles which we discovered should be no surprise. From previous science classes, you know that the existence of protons, neutrons, and electrons are the particles which make up the interior of those atoms. And as it turns out, the first of those subatomic particles discovered was, not surprisingly, the electron, given that you guys have probably seen direct evidence of the existence of electrons when you see things like static sparks or shocks. So, the experiment which was used to prove the existence of the electron is an experiment produced by Joseph John Thomson, or J.J. Thomson, back in the year 1897. And the experiment which he did here was what we refer to as a cathode ray tube experiment. Now, in that cathode ray tube experiment, what he essentially did was he took a device in which there was a separation of charge, and that separation of charge built up a large number of electrons, or really charged particles, on a metal plate. And so he had a negatively charged plate separated in space from a positively charged plate. And because opposites attract here, those negatively charged particles on the negatively charged plate would fly through space towards the positively charged plate inside of this vacuum tube. And in the center of that positively charged plate was a little tiny opening. And that little tiny opening in the center of that plate allowed some of those particles to fly through the opening into the rest of the tube. And as they flew through that opening, they would pass through the tube and then through another set of charged metal plates, one of which had a negative charge and the other of which had a positive charge. And the key finding from this experiment was that when those particles flew through those two metal plates, they would deflect from their original path. And they deflected away from the negatively charged plate and towards the positively charged plate, which told Thomson that whatever that particle was that was flying through space inside of these vacuum tubes must have been a particle which was negatively charged itself, having been deflected by the negatively charged plate. And furthermore, by looking at the degree of the deflection, that is the angle by which those particles were deflected, Thomson was able to determine the ratio of the charge on the particle to the mass of that particle. We call that the charge to mass ratio of the particle. And he named that particle the electron. So we've got our first subatomic particle determined to be existing within the atom from this experiment. And from that, we're going to take our model atom developed by Dalton and modify it. We know still that atoms overall are neutrally charged. However, we know within those atoms there must be these particles that can be produced through the cathode ray tube experiment. And so we've got some negatively charged electrons embedded within the overall matrix of the atom. And because the atom overall needs to be neutral, that implied to Thomson that there had to be some positive charge, which he distributed uniformly throughout the remainder of the atom. So what we have here is kind of a model atom that looks like what he referred to as a plum pudding model, where this is kind of a popular dessert back in the day, where you had kind of a positive gooey matrix of the pudding with little raisin electrons embedded within it. A more modern kind of dessert analogy here would be this is like a chocolate chip cookie model atom, where the electrons represent the chocolate chip cookies, and then the remainder of that atom, the cookie matrix, is the positively charged goo throughout. Now, as it turns out, this experiment had some fairly big implications for the real world later on. These cathode ray tubes are what we use to develop the first televisions. So that television, the old big CRT TVs, really are nothing more than cathode ray tubes that you saw back before we had flat panel monitors. So we now know of the existence of electrons. Moving on next from this experiment, we're going to talk a little bit more about our understanding of the electron. The next experiment that was performed by a gentleman by the name of Robert Millikan back in 1899. Now, whereas Thomson's experiment determined the ratio of charge to mass of the electron by looking at the degree to which it was deflected within that external electric field, Millikan was able to determine the actual magnitude of the charge on the electron. And knowing the magnitude of the charge on the electron, together with the charge to mass ratio from Thomson's experiment, he was actually able to determine the actual mass of the electron to be 9.11 times 10 to the negative 31st kilograms, which is a fairly remarkably small mass, especially to be measured with technology available back in 1899. In order to make this discovery, Millikan performed what we refer to as the oil drop experiment. In the oil drop experiment, Millikan started with a essentially empty container, and in that empty container, he injected a number of particles of very, very fine mist of oil into that chamber. And as those particles were injected into the chamber, they passed by essentially little tiny brushes, and those brushes were able to knock off electrons off of those oil droplets, leaving all of these oil droplets with a positive charge. So we essentially have a bunch of positively charged droplets of oil suspended inside of this container. And then that entire container was then subjected to an external electric field. That is, he put some plates around the outside of the container, and then he put a positive charge on one side and a negative charge on the other side. And what he then looked at was essentially a balance of forces. He adjusted the relative charges on those plates to the point where the force of gravity pulling downwards on those oil particles exactly balanced out the force of electrostatic repulsion on those positively charged particles from the positive plate down below. And we'll call that force of electrostatic repulsion. Now, because he could measure the mass of the oil droplet particles, he therefore knew the force of gravity acting upon them. And if he knew the force of gravity acting upon them and those two forces were balanced, that implied he also therefore knew the force of electrostatic repulsion, which was supporting the particles floating around inside of this tube. And by applying essentially Coulomb's law, which again tells him that the force of attraction and repulsion between charged particles is equal to a constant times the products of the charges divided by the distance separating those charges squared, knowing the force of repulsion acting on the particles, and also knowing the charge that he had put onto the metal plate, and the distance which separated the plate from those charged particles, essentially he could apply Coulomb's law to solve for what the charge must have been on those oil droplets. And he determined that those charges were always a whole number ratio of some fundamental incremental unit amount of charge. And that charge happened to be the charge on a single electron. And knowing that charge, he was then able to determine the mass of the electron as well. So at this point now, we have information about both the existence of the electron, its charge to mass ratio, and its individual charge and mass. So we can move on to our next subatomic particle. The next discovery we're going to talk about here is a discovery made by the chemist Lord Ernest Rutherford, more of a physicist, I guess, than a chemist, from New Zealand back in 1909. Rutherford was able to discover the existence of the nucleus of an atom, and not only that, he was able to determine that that nucleus must have been three things. Number one, small. Number two, very, very dense. And number three, positively charged. And because of the discovery that most of that mass of the atom was concentrated in one very, very small region in space, that implied to Rutherford that in fact most of the atom was made up of nothing more than empty space, whereas there was a very, very small concentrated amount of matter at the center. Now, this was a very big departure from the understanding that had been put in place by the Thomson model atom with the plum pudding model that was described earlier, where the mass of the atom was essentially uniformly distributed throughout the entirety of that plum pudding model there. So we're essentially going to take that plum pudding model and shrink most of the mass down into one tiny, tiny area in the center. Now, the understanding that came out of this came about as a result of an experiment that Rutherford performed, which we refer to as the gold foil experiment. In the gold foil experiment, Rutherford essentially took a source of alpha particle radiation and concentrated that alpha particle radiation into a small beam by passing it through a little tiny hole in a container. And then that beam of alpha particle radiation was then aimed at a piece of gold foil. Around the outside of the gold foil was a screen, which was a phosphorescent screen that would kind of light up when it was struck by an alpha particle. And what Rutherford had hypothesized was going to occur during the course of this experiment was essentially that those alpha particles should fly right through the very, very, very thin piece of gold foil. Because on the atomic scale, that gold foil is more or less like atomic scale tissue paper, and those alpha particles are like little tiny atomic scale bowling balls. So his thought process was that by shooting alpha particles at the tissue paper, he should essentially see them rip right through, pass through it, and hit the detection screen immediately behind the gold foil. And most of the time, that's actually is what happened. However, in the course of performing his experiment, he noticed that every once in a while, when those alpha particles were emitted from the source, instead of passing through the gold foil as expected, sometimes they would either be deflected or they would bounce back. And that was a very surprising finding to him. Kind of the same way it would be surprising to you if you shot a bowling ball at a piece of tissue paper and that bowling ball bounced right back and hit you in the face. And in order to account for the fact that sometimes those particles were deflected, he had to change the model understanding that we had of the atom. That is, these atoms couldn't be made up of diffuse mass uniformly spread out across the atom because those alpha particles would rip right through that. Instead, there had to be something that was inside of the atom that was really incredibly, incredibly dense and incredibly, incredibly hard and massive. And that massive particle inside of the atom, he referred to as essentially the nucleus, or the center. Now that justified for him then the results of his experiment because he was able to determine that, in fact, most of the alpha particles should have passed right through without touching anything, exactly as he had predicted. But then every once in a while, when one of the alpha particles, themselves being positively charged helium nuclei, came into contact with the very, very small, very, very dense, and positively charged nucleus, it will be deflected from it due to the repulsive force between those positive charges. So again, we now need to, from these experiments, determine a new model of our atom. And the Rutherford model atom took essentially the plum pudding model, where that positive charge mass was uniformly distributed throughout the entirety of the atom, and shrunk it down to the point where all of that positive charge was found in one very, very small spot in the nucleus of the atom. And we still had those electrons floating around the outside. So this is now what we refer to as the Rutherford model atom. All right, moving along next. We've got a new experiment here. We're going to kind of take a little bit of a departure here. Instead of looking at the existence of the final subatomic particle here, that is the neutron, which we still haven't found yet, we're going to kind of look and refine our understanding a little bit about how these atoms are built up. And the discoveries from this experiment, actually, as it turns out, fundamentally help to change our understanding of how the world works. Back when we had proposed the original models of these atoms where those electrons were just kind of distributed at random throughout the plum pudding model, or in the Rutherford model, we had this idea that really you could put an electron anywhere inside of that atom. That is, anywhere in separation away from the nucleus, which would give those electrons any random amount of potential energy. But by an experiment, which in fact you will be looking at in class, Niels Bohr was able to determine that those electrons actually were not able to be placed at any potential place within the atom itself. They only existed within certain specific energy level shells or layers within that atom. And each of those different potential energy shells or layers could only accommodate a specific number of electrons. And this is really what we refer to as the dawn of what we call quantum mechanics. That is, we're going to kind of depart from our understanding of physics from the idea that you can put things at any potential energy you want them to, and instead move to a place where energy is itself quantized. That is, it comes in discrete unit amounts. Only specific allowed amounts of energy are possible within the atom. And the experiment which he performed in order to determine this was the emission spectra experiment. And that emission spectra experiment is the one you do in class, in which you will be observing that there are discrete lines of color produced by the emission of photons of light from excited electrons within atoms of different samples of matter. And so because only specific colors of light, only specific frequencies of light are emitted, that implies only specific energies of light are emitted from these atoms. And if only specific energies of light are emitted from these atoms, that would imply, therefore, to us that only specific energy levels are allowed for those electrons inside of those atoms. So from this idea, we're going to go ahead and now modify our understanding from the previous Rutherford model of the atom to now what we refer to as the Bohr model atom. And in that Bohr model atom, rather than having those electrons placed randomly like they had been traditionally from the plum pudding model, instead we're now going to put those electrons into discrete energy level shells where there's only specific numbers of electrons allowed and permitted within each of those different shells. And this is now where we get to our Bohr model atom, that is the quantum mechanical model of our atom. And moving along from the Bohr model atom, we're going to get to our last subatomic particle. Not surprisingly, the last particle discovered was also the most difficult to discover because this particle itself is neutral. And neutrally charged particles do not interact via electrostatic repulsion or attraction, which was more or less the tools that we'd use to discover the proton and the electron. So the discovery of the neutron came about as a result of some experiments performed by James Chadwick. He discovered, in fact, that if you bombard beryllium with alpha particles, those beryllium atoms will produce a stream of neutrally charged, penetrating and non-ionizing radiation. And as it turns out, if you take those particles produced by the beryllium as it's bombarded with those alpha particles, and you perform some essentially momentum calculations using kinematics, very similar to what many of you have done in your physics days, looking at kind of two-dimensional or three-dimensional conservation of momentum problems. He was able to kind of work his way backwards through some of these nuclear collisions to determine the actual mass of these particles to be very, very similar to the mass of protons. And so from this evidence that there were neutrally charged massive particles present in the nucleus of the atom, Chadwick was able to come up with our last of our subatomic particles within the atom and kind of come to a more complete understanding of the modern atom as of the 1930s. And so we're going to look at the last model atom we have here. In that Chadwick model atom, essentially all we're going to do is take what had been the Bohr model atom, where we had the positively charged protons present in the nucleus, and instead change this to now a model atom where there are both positive charged particles and neutrally charged particles present in the nucleus together. So it looks just like the Bohr model atom, but now with neutrons present as well. And that brings us to our understanding as of the beginning of the 20th century of our atomic theory. And we'll pick up this lecture next as we discuss modern atomic theory on our next lecture. Thanks for listening.